Okay, it's time to start. Good afternoon, everybody here in Poland or Europe, wherever you are. And good morning to our friends on the other side of Atlantic, and to Ben Whitney, who is our speaker today. My name is Marek Michalewicz. I'm the director of Interdisciplinary Center for Mathematical and Computational Modeling at the University of Warsaw. I have a pleasure of hosting very interesting speakers at our virtual ICM seminars in computer and computational science. We started running those seminars last year around March, April, right after our Supercomputing Frontiers Europe 2020 conference. We've learned to sort of use the new format of a virtual communication and conference and seminars. And we also noticed that it gives a much wider reach, and we can invite people from all over the world to speak at our seminars. We bring speakers to our audience in Poland and sometimes feature Polish speakers to the worldwide audience. So it benefits us most certainly. Of course, in order to run this sort of enterprise, we have partners. So we have honorary patron in with the National Information Processing Institute in Poland, and several media partners which help us promote this event. These are Datanami, HPCY, Enterprise AI, ITWiz, and Computer World. I have a second slide, please. I have control over slides. So, as I said, there were already 14 seminars, and all of them are recorded. So for those of you who are for the first time attending this series and are interested in various other topics, and I can vouch that every single lecture this series was extremely interesting, fascinating talks. Here you have 3 speakers featured. Stephen Wolfram, Hierarchical Kitano, and David Bader. These are last 3 that we had. Of course, there are many others. Please, if you have interest and some time, please browse through this link, our website, and you will see that indeed we have very, very fascinating speakers. Of course, including Ben today. Might I have the next slide, please? Yeah, maybe I can. So I would like to announce the next talk in March. The next talk will be given by Valery Polichar, who is Senior Director, Academic Technology Services and IT Service at University of California, San Diego. And the tentative title is Digital University. And I need to make a disclosure. I've very deliberately asked Valery to talk about this because ICM is embarking in changing the profile of our services. We are moving, we're not leaving HPC field, but we are expanding into cloud services and research cloud services for the university and several other universities in Warsaw and in Poland. So we'll be expanding, changing the way we work, and in a very substantial way, expanding our user base. And the University of California started this process about 2009. They have very good experiences, and this, to me, it's a sort of exemplary case of how certain research services at the university should be run. So I encourage you all, and please share it with your colleagues, especially in at the level of university. That is a very interesting talk, I believe. Then I would like to announce our 7th edition of Supercomputing Frontiers Conference, Supercomputing Frontiers Europe 2021, which will take place virtually again on July 19th to 23rd. The conference, there's a website, and we've already opened for CFP, so please check the website, this website, and If any of you is interested in submitting paper, or perhaps share it with your colleagues in your circles, we welcome all sorts of interesting papers from around the world. I won't be talking about program of this conference. I will be doing this closer to the date, and of course, the website will have more of it. And today, moving to today's talk and our speaker, we're very happy to have Ben Whitney with us, who is a postdoc in the Computer Science and Mathematics Division at Oak Ridge National Laboratory. As we all know, lots of breakthrough ideas and tools and methods and technologies are being trialed and discovered and prototype at Oak Ridge National Laboratory. That's a place to look for in supercomputing field. So we are very glad to have Ben Whitney. Ben received his PhD in applied mathematics from Brown University under the supervision of Mark Ainsworth. And after graduating in 2018, he took a postdoc position at Brown and then came to Oak Ridge National Laboratory in 2019. And he works in compression methods for scientific data and scientific software development. Of course, for many, that topic might be marginal, and until you really had a face-on clash collision with humongous data, you don't appreciate how important this topic is. And of course, if we are talking, small time research in many fields, it's perhaps beyond your horizon. It's not in your sphere of interest. But if we are talking about things like square kilometer array or large radio telescopes or telescopes or the biggest scientific instruments operated around the world, those methods and what Ben will be talking about is absolutely crucial. So with that introduction, Ben, the floor is yours. Thank you very much.
Thank you. Okay. Hi, everyone. My name is Ben Whitney. As Mark said, I'm a postdoc in the Computer Science and Math Division at Oak Ridge National Lab here in the US. I'm going to be talking today about MGARD, which is multi-grid adaptive reduction of data, which is a tool for hierarchical compression of scientific data. Okay, so first I want to thank my collaborators. So here's who worked on this project at Brown University. We have Mark, my former advisor, and Ozan, Missouri Science and Tech, Shin, New Jersey Institute of Technology is Ching or Gary, and here at Oak Ridge, Rick Archibald and Scott Klaske are group leads, and Jaeyoung Chin and myself are members of their groups. Okay, so first I want to motivate a bit who might be interested in data compression. So the way I see it, there's sort of two groups. The first group are computational scientists who don't yet use data compression, but may have to with the next generation of machines. So for example, maybe they deal with fairly large data sets, but they have found workflows that work for them, and they're able to deal with the volume of data they have without too much imposition. But here I have pictured Frontier, which is the exascale computer that's going to be delivered to Oak Ridge this year. And so maybe the same workflows that worked when you had, say one terabyte of data, say, maybe won't work so well when you have 10 or 100 terabytes or a petabyte. So maybe there's various places in your workflow that I can imagine you running into issues. One, simply you could run out of disk space. Maybe you have enough disk space, but with your local cluster, an analysis that used to take overnight now is starting to take days or a week, and it's really starting to impede your progress in doing the science you actually want to do, rather than just wrangling with the data. Or maybe you have collaborators, say, overseas, and the network between you is not robust enough to support you sending terabytes every day to each other. Okay, so then the second group of people that I think this sort of topic of data compression might be of relevance to is computer scientists who, or computational scientists who already use data compression in one form or another. And actually, I find that a lot of modeling and simulation people actually are already at that stage. So for example, if you have some time stepping simulation, some time stepping computation, maybe your time step is dictated to you by some stability conditions, some CFL conditions, something like that. And you might like to save every time step of your simulation, but you'd quickly run out of disk space. So you decide on some decimation stride, you say, I'm going to just write out every 100th time step or every 1000th time step. So doing that is a sort of ad hoc compression method. You have a compression ratio of 1,000. You don't have great error bounds because the time steps you aren't writing, you're just throwing away. So you don't really have a measure of how much you're throwing away, although you may have some physical understanding of sort of physically what's going on and the scales, and you might have a good degree of confidence that you're sort of like resolving the physics that you're interested in. A similar sort of ad hoc approach, but also that is sort of commonly used, is just truncation from double precision to single precision. So maybe you have some iterative method and you need double precision for convergence, but you actually don't think that you have a double's worth of accuracy in your end data, so you truncate to float before writing out. So that's a compression method. Compression ratio of 2, a float is half the size of a double, and here you actually have a pretty good idea of the error you're incurring, because it's like the amount of precision that a double can represent that a float can't. So for these people, the sort of question is, they're already using compression. They're already somewhat comfortable with losing some small amount of fidelity in their data. And then the question is, can we give them something that improves on these ad hoc methods that they're using? Okay. So next I want to talk about broadly some sort of like a sort of wish list, some properties we might like in a scientific data compressor. MGARD can't do all of these yet. These are just sort of directions we're headed with. Something I want to focus on is mathematically guaranteed error bounds. So this ends up being actually a lot of thought ends up going into how you want to measure the compression error. So the sort of initial approach we started with, the sort of naive approach, is to try to control the pointwise error of the compression of control the compression error pointwise. So for example, someone might have a simulation, they run into convergence. So the data that they give to the compressor is pointwise accurate to within 10 to the minus 12. And so maybe the natural thing is to say, okay, I'm going to try to give back something that is accurate pointwise to within, excuse me, 10 to the minus 9 or something like that. And MGARD can do that. Other compressors can do that, but I don't know of any compressors that can give you something like pointwise error of 10 to the minus 9 and achieve any real compression. It's just a much too tight error tolerance. And in fact, it's kind of a mismatch with how the data is actually being used. So no one is writing out a terabyte of data and then their analysis consists of looking at individual values. So not looking at the value of some function at a particular node in their mesh and making any sort of scientific decision from that value. Instead, people are computing derived quantities. Maybe they're looking at the moments of their data. Maybe they're computing some flux integrals. They might just be visualizing the data. And so what we'd actually like is to compress the data in such a way that these operations, these sort of like derived quantities that people are using their data for, that when we conduct these operations with the compressed data, we get to within some small error tolerance, the same thing we would get when we use the original data. So for example, if you're visually checking for some feature, it's there in the compressed data, it's there in the original data. Okay, so now let me give just a brief overview of how MGARD works before sort of diving into the details. So MGARD could be classified as a transform-based compressor. So the general workflow is you start with your original data. It's going to be some function defined on a mesh. It's for like field data. And the first step is to apply a transform to it. So we transform from the original nodal values of this function to coefficients in some transformed basis. And then it's with these transform coefficients that we're actually going to do the actual compression. So first we're going to quantize the coefficients. So we round each of them to nearest multiple of some small number, incur some rounding error. And then we take those quantization labels and we pass them to some off-the-shelf, for now, lossless compressors. So it could be something like zlib. Zlib is it's a entropy encoder. It's the algorithm that is used in gzip. If you've ever gotten like a .gz file, it uses zlib. So there's many other transform-based compressors. I think maybe the most famous one is Jpeg, the image compression algorithm. So the way Jpeg works is you take your picture, your array of pixel values, you split it up into little squares. I think it's 16 by 16, and then you apply a discrete cosine transform to each of those squares. So you transform from pixel values, the like color values, to coefficients in this discrete transform, discrete cosine transform, and then you apply a filter to those transform coefficients. So roughly, you keep the low modes and you discard the high modes. You say the high modes, the very oscillatory sort of functions, are basically noise. and you keep the low modes, and then you compress the result, and then that's your .jpeg. So anyway, we're sort of following a similar model. So for the rest of the talk, first I'm going to spend some time talking about the transform that we use, both what it is and then a little bit about implementation details. And then later I'll talk about this quantization step, because that's where we incur our error, and that's where we need to make sure that we're not messing up any sort of scientific analysis that's going to be conducted later on the data. And then finally, I'll show some numerical examples. Okay, so first let's talk about the setting. As I said before, the sort of domain of MGARD is functions defined on meshes. So in addition to it being a function defined on a mesh, we require one important property. We're assuming that the mesh PL that our data U is defined on sits on top of a hierarchy of nested meshes. So here, this blue mesh would be the mesh that our data is actually defined on, but we get to our blue mesh by starting with some initial very coarse mesh. This would be P0. And then we refine P0, the purple mesh, to get P1, the red mesh. It's nested, right? So it's just a sort of a refinement. And then we would continue doing that over and over and over until we reach the desired resolution. Here, there's just one more level, the blue mesh. And then it's on this final mesh that our data U is defined. This requirement is a little more strict in this sort of case of triangulations, because a lot of times you might not like your triangulation to look like this. In the case of like rectangular data, which a lot of the examples would be, this is like a pretty modest condition, because you can always just define a submesh of like the final mesh. Okay, so now let me sort of talk about the transform and what the coefficients will be quantized and what they actually are. So the first step of the algorithm, we take our original data U, it's like a function defined on this mesh, and we want to transform it to something called the multi-level coefficients. These are our transform coefficients. So the multi-level coefficients, it's an array of the same size as our original data U, and to each node X in the fine mesh, we have a single coefficient that's defined as follows. So we start with our data U, and we first project it, take the L2 projection of our original data U onto each of the meshes in the mesh hierarchy. So this alternatively increasingly fine or increasingly coarse hierarchy of meshes. So we compute an L2 projection for each mesh. We then take the, so that's QL of U, L2 projection. We then take that projection and we compute the interpolant of the projection onto the next coarse mesh. So this pi L, it's a piecewise linear interpolant. So in one dimension, we have our projection, QLU is just some piecewise linear function. The interpolant onto the level below, basically we just forget about every other node. I'm gonna have a picture in a couple slides. Basically, we forget about every other node and we just connect the dots. So it's just a piecewise linear interpolation, that's all. Then we're gonna find the difference of the projection and its interpolant. So then we take that difference, which, let me also just get my cursor. Okay, I think it says you can see my cursor. So that's this function here. Later, I'm going to call it a multi-level component, but it's the projection onto a given level minus the interpolant onto the level below. So we take that function, we evaluate at a subset of the nodes in the given level. So here, the nodes that we evaluated are the nodes that are new to the current level. So if we're at mesh level L in the hierarchy, these are the nodes that are present in mesh level L, but not present in mesh level L-1. So when you refined the mesh, it's the nodes that you added. So we evaluate this function, this difference. At these points, we write those out. Those are the multi-level coefficients for this level. Then we're going to continue to the level below and until we have all the multi-level coefficients. So right here is an overview of how that's actually done. So to start with, we need the projection of the data onto the finest mesh. That's just the data. We don't even need to calculate that. So then we now, in this loop here, for each level in the mesh, we're going to do the following. We start with the projection. We interpolate, get the interpolation onto the level below. Then we subtract one from the other. This is our multi-level component here. This is the thing that we need to evaluate at the new nodes in the current level. Those point evaluations are the multi-level coefficients for this level. So we write out all those multi-level coefficients. These next two lines I'm basically going to skip over, but we then need to do some sort of transformation in order to obtain the L2 projection onto the level below. So the details aren't important, but this is sort of the bulk of like the algorithm, the time required to actually do the compression. The slowest things are the the lossless encoding, and then these projections. This is sort of what mechanically is being done. Okay, so now let me show just a picture so you can visualize what's going on. So again, for each level, we start with the L2 projection, we convert it into multi-level components, which are multi-level coefficients. It's sort of the same thing. One is a representation for another. I'll get to that in the next slide. And then the projection onto the level below. So all right, so in pictures. We're at level L. Here's our projection onto that level, this purple function. It's a piecewise linear function. It's given by the nodal values at the nodes present in the given mesh. So the first step, compute the interpolant. Since we have the projection by its nodal values, it's really sort of no calculation at all. We just remember every other value. So the blue function on the right here, that's the linear interpolant onto the level below. We basically just forget about the value in the middle. We then need to find the difference of the purple and blue functions, the projection and the interpolant. So let me skip one more. So at the nodes, at the left-hand and right-hand nodes, these are the nodes that are present in the coarser mesh. It's like the nodes we're interpolating on. By definition, the interpolant is equal to the function it's interpolating, so the difference is always 0. So you can see on the left here that this orange function is the multi-level component. It's the function that we evaluate to get these multi-level coefficients. It's automatically 0 on the left-hand and right-hand nodes. These are basically the nodes that we don't store the values of this function because we know that they're 0. So the only place in this example that we're storing a value is the central point here. So this xj plus 1, this is present in the fine mesh, which has the 3 nodes on the left. It's not present in the coarse mesh that the interpolant is defined on, which only has the left-hand and right-hand values. So this value here, this difference, that is a multi-level coefficient. So it's a difference of these two functions evaluated at a particular point. Okay, so that's how we get the multi-level coefficients. Now I want to give a little bit of motivation as to sort of how you might think of them, what they sort of mean. So in the slide after this, I'm going to give a sort of a decomposition of you in terms of multi-level coefficients. For that, I need these 3 equations. I'm just going to summarize them. You don't really need to worry about the details. So this first equation, it's an orthogonal decomposition of U using the mesh. So we can write U as a sum of the following. For each mesh in the mesh hierarchy, we take the L2 projection onto that mesh. We subtract out the L2 projection on the level below. That's called an orthogonal component. Each of these orthogonal components, they're mutually orthogonal because I won't go into details. They're mutually orthogonal. They sum to U. It's a telescoping sum. So it's just a decomposition of U. Now we can we can obtain each of these these orthogonal components, the difference of projections, from the multi-level components, which is the same thing except you're subtracting off an interpolant rather than a projection onto the level below. So turns out you can do this by taking the multi-level component and subtracting the projection to the level below. Again, the algebra doesn't really make a difference, just you can go from one to the other. And then finally, we can take these multi-level components and we can express them using the multi-level coefficients, expand them in what's called the nodal basis. So the multi-level component is a piecewise linear function. We can, it exists on a certain mesh and it's piecewise linear on that mesh. So we can span the space of piecewise linear functions on that mesh with something called the nodal basis. So it's the nodal basis functions are piecewise linear functions. They're 0 at every node in the mesh except for 1. So phi L here is 0 at every node in level L except for at x. So it looks like we call it like a hat function. It looks like a little hat. And so the coefficient of a function corresponding to like a particular hat function is just the value it takes at like the corresponding node, the node that the function is 1 at. So so in order to expand our multi-level coefficient using these hat functions, we just the basis coefficients are just the values here, this red value, the values taken by the function at the points in the mesh. And by definition, that's just what the multi-level coefficient is. So you can think of the multi-level coefficients here as the coefficients with respect to this basis of these components. Okay, so anyway, the details there, don't worry about them too much. They are just combined in the following to give a sort of intuitive explanation of what the multi-level coefficients are. So we start with our data U, we decompose it using this orthogonal decomposition. We rewrite each of the orthogonal components using the multi-level components. This was the second equation. And then we expand each of the multi-level components, this thing on the right, the projection minus the interpolant on the level below, and we expand it using the multi-level coefficients with this nodal basis function. So then we just, we're going to reorder the sum, and we find that the multi-level coefficients are the coefficients for u with respect to the basis, with respect to this particular basis. So the basis, the red function, has the following form. It's a hat function, a nodal basis function on a particular level. So again, 0 at every node except for 1, so it's a little spike. And so that's phi L. And then we compute the L2 projection of phi L onto the level below and take the difference. And so then here, this function I've plotted is one such sort of wiggle. And it's sort of reminiscent, hopefully, of a wavelet. It's spectrally supported in a small region of the spectrum. Though it looks like it also has a compact spatial support, it's actually not the case. It actually has global support. It does decay down to 0 exponentially quickly. So it's sort of, you win some, you lose some. Okay, so now we've talked about the multi-level coefficients, what they are, how we calculate them, and then also hopefully a way of thinking about them. Each multi-level coefficient is the weight of a function that looks like this in the expansion of our original data U. So it hopefully captures like variation of some scale, some frequency, and in some spatial location. Okay, so now before I talk about truncation and the actual doing the compression, I just want to sort of nod at a couple like implementation issues. So everything I've shown you so far, all the pictures at least, have been about how this is done in one dimension, where you have piecewise linear functions defined on some one-dimensional mesh. So in 2 dimensions, we have to decide how we're going to define our function spaces. That dictates how all of the operations we need to do will be conducted. So the L2 projection, the interpolant are the main ones. So the decision we make is to define, for example, in 2 dimensions, our 2-dimensional function space would be the tensor product of piecewise linear function spaces in x and y dimensions. So as a result, our 2-dimensional function space is it's a continuous piecewise bilinear functions. But yeah, just obtained by a tensor product. The advantage of this is that all the operations we need in order to compute the multi-level coefficients, so mainly it's these L2 projections and the interpolations. If we're doing, for example, an L2 projection onto a tensor product function space, it can be the L2 projection, just as the function space is given by a tensor product of one-dimensional function spaces, the 2-dimensional L2 projection is given by a tensor product of one-dimensional L2 projections. What this means is that in applying the 2-dimensional L2 projection, we can decompose it into these one-dimensional projections. So here on the right, we have this a 2-dimensional grid. And the red arrows represent an L2 projection in the y direction. The blue arrows represent an L2 projection in the x direction. And so in order to achieve the 2-dimensional L2 projection, we never need to do any operations with all 25 nodes at the same time. Instead, we first do 5 parallel L2 projections in the y direction. Each of these, they touch completely different nodes, so they're totally independent. They can be conducted at the same time. We first do all the 5 y one-dimensional projections, then we turn around and do the 5 x, the blue L2 projections. So we have a sort of natural structure that we can use to parallelize the main operations of our algorithm. And so, yeah, in fact, this is something that we're working on currently, is a porting of our original CPU implementation to GPU, and it's taking advantage of this tensor product structure that like makes it possible. Okay. And then one more sort of implementation note. So I had mentioned before that we calculate the multi-level coefficients level by level. So for each level, we start with the L2 projection, calculate the interpolant, take the difference, do these point-wise evaluations. So in principle, the first level should be the slowest. It involves every node, every value of the original array. And then as you go down, your meshes are getting smaller and smaller. Your operations are being conducted on fewer and fewer nodes. So hopefully, this would be a sort of n log n operation, because as you proceed down to the mesh hierarchy onto coarser and coarser meshes, you're doing operations involving fewer and fewer nodes. Unfortunately, yes, you're operating on fewer and fewer nodes, but these nodes are farther and farther apart. So you actually you end up spending a long time waiting for your values to come from the cache. So let me sort of describe in pictures. On the left here, we have the sort of pictorial representation of a mesh hierarchy. So the red nodes would be our coarsest mesh here, these 4 points. The red and blue nodes together would be the refinement of it would be P1, the next finest mesh hierarchy. And then the red, blue, and white nodes together would be the finest mesh. So if you're doing an operation on just the red nodes on the coarsest mesh, Yes, there's only 4 nodes, but you're going to have to read through the entire, you have to read through all the white and blue nodes that sort of stand between the like quote unquote adjacent, like logically adjacent red nodes. So actually in doing these operations, yes, there's very little sort of arithmetic work to do, but you end up sort of spending all your time just waiting for values to come to you. So the way we sort of get around this is we add a step before the transform. We rearrange all the values according to so that values corresponding to a given mesh, for example, the courses mesh, are adjacent in memory. And this so this is an added cost. We have to like first we have to do the shuffling operation, and later we're going to have to unshuffle. But it does mean that when we are doing operations on relatively coarse levels in the mesh hierarchy, all the values are adjacent in memory. So it ends up speeding up the whole algorithm quite quickly. Okay, so these are just 2 sort of performance implementation issues we've run into when trying to improve the speed of the algorithm. Okay, so now we've talked about what the transform is, a little bit how to sort of interpret the multi-level coefficients, how to think of them. They're the weights of these sort of wavelet-like functions. So now I want to talk about how we actually use the transform coefficients to compress. So as I said before, the basic workflow is we start with our original data U. We do the transform that gets our multi-level coefficients. That's in the upper right here. These are our multi-level coefficients. We're then going to quantize them, round them, incur some error, and get these U twiddle MC. So it's multi-level coefficients for some compressed sort of perturbed function U twiddle, which is hopefully very close to U. We'll take the quantized coefficients, later pass them to a lossless compressor. That's where the actual reduction in number of bytes happens. But then if we want to decompress this set of quantized coefficients, we basically we expand from the gzip or whatever. We run g unzip, get our quantized coefficients, then we do the inverse transform, and so that brings us to this function u twiddle, which hopefully is not too different from u, and it's in the original degrees of freedom. It's just a function defined on the original mesh. So unfortunately, there is a little bit of a disconnect here. So what we would like when we do this whole process for the error in the original degrees of freedom, I mean the error like as a function between u and the compressed representation u twiddle, we would like the error there to be small. So that's where we care about our artifacts. That's where we want things to be indistinguishable. But that's not where we're doing our operations. We're doing our operations on the right side of the diagram here. So the place we actually make our changes is in the multi-level coefficients, these transform coefficients. And so we're quantizing them. So for example, we represent each as a multiple of some small number epsilon. So when you do that, you incur you incur an error of at most epsilon over 2. So it's very easy in terms of the in the world of the multi-level coefficients, it's easy to say what your error looks like. So you can say like I quantized with sort of step epsilon, my maximum error is epsilon over 2. And I have, say, n coefficients, my total error is like n epsilon over 2, or you can do total square error or whatever it is. And so you might quantize in such a way that your total error is very small. But that doesn't necessarily tell you that your error in the original coefficients on the left-hand side of the diagram here, that when you decompress and actually compare the functions one to another or try to compute something with them, it doesn't actually tell you that the error there is going to be small. So what we need is some way of relating changes made to the multi-level coefficients, if we truncate them, if we quantize them, whatever it is. We need to relate errors made there to errors in the original degrees of freedom, to functional errors. And then that is how we're going to be able to get our error bounds in terms of like the original data, which is where we care about the error. Okay, so the way we do that is using something called an estimator. The idea comes from finite element analysis. There are error estimators used there. So to start with, we have this family of norms, this norm index with an S. Actually, I can point with my pointer here. These are the norms that we're going to use to measure the error in the original like coefficients of the data as a function. So here, this is a norm that was defined in the finite element analysis community. The reason we use it is that let's see, it's a family of norms parameterized by the smoothest parameter S, and you get various useful norms depending on the value taken by S. So for example, if S is equal to 0, this is just the L2 norm. If S is equal to 1, this is the H1 norm. So it's the L2 norm on the nodal values plus the L2 norm on the gradient. So if we had some operation that required that the gradient of our data was preserved, we could compress the data so that the S is equal to 1 norm was small. That would of the error was small. That would tell us that the H1 norm of the compression error was small. It would mean that we would have resolved the gradient within some epsilon. Okay, so then for each of these norms, we have a corresponding estimator. There's a thing on the second line that's eta s. So the estimator is again a norm, and it differs from the norm only in the term here. So rather than the orthogonal component here, which is what's used in these sort of well, Sobolev-like norms, they're equivalent to the Sobolev norms. Rather than the orthogonal component, we have the multi-level component. So this is the thing that's encoded by the multi-level coefficients. When we have the multi-level coefficients, we basically have this thing in hand. So it means when we have the multi-level coefficients, if we make some change to multi-level coefficients, it ends up being quite easy to estimate the change as measured by this estimator, because we're sort of like talking in the same language. We have the right sort of coefficients at hand. This is helpful because we can show that this estimator, the thing on the second line, is equivalent to the norm. So what this means is that if we change the multi-level coefficients in such a way that the error as measured by the estimator is small, we have a guarantee that the error as measured in the original norm, this S norm, which is like, say, the L2 norm, will be also small. It'll be like bounded by a constant times the estimator. So this is how we get our error bounds, basically. So sort of this estimator sort of theory leads to sort of actionable algorithms that look something like this. So this is a theorem that assigns to each multi-level coefficient there's a particular weight. The weight is calculated using first the estimator, and then it's the estimator, and then we measure how much each individual coefficient contributes to the estimator. That's sort of another step I'm not showing. But the end result is that each multi-level coefficient gets a certain weight, and that weight gives a bound on how much errors made to that multi-level coefficient in the quantization process will translate to sort of functional errors. And so if the weight is very high, that's telling us we need to quantize very accurately, because if you make too large of an error, you're going to use up your error budget. You're going to sort of, your compressed function utwiddle won't be as close as you asked to your original function. On the other hand, other multi-level coefficients will have relatively small weights. That's telling us that we can afford to quantize much more aggressively, because even if we make a moderately sized error in that particular multi-level coefficient, it's not going to translate to a large error in the original data. So that means we can quantize more efficiently. We can get a better compression ratio for that subset of the multi-level coefficients. Okay, so next I want to show how this actually comes out in practice. So I'm going to do some, let me see how I'm doing on time here. I forget exactly when I started, but maybe about half an hour. So maybe I can afford to go just a little bit slower, I think. Okay, so first we're going to compress the results of a numerical simulation. This is going to be a simulation of something called a brucillator, which is a dynamical system, a model of a chemical oscillator. So our domain here will be just like a petri dish. You can see videos of this type of thing on YouTube. You have a sorry, I have one slide before the video, if that's okay, Christoph. Sorry, I should have asked. Sorry. Thank you. Yeah. So I do have a video. Okay, so then we have these two chemicals that exist in solution in the petri dish, and they react with one another in this sort of cyclical reaction. The reaction doesn't go straight to equilibrium; they sort of like cycle. Okay, so in the video that we're about to see, every frame of the video is going to look like this. So I want to first explain what each of the plots mean, so that you can sort of like understand what's happening in the video. So excuse me. In the upper row, we have an illustration of the concentration of one of these two chemicals in the reaction. So upper left is the original concentration at a particular time step. So then going to the right, it's the result we get when we compress and threshold the multi-level coefficients. So we only keep n of them. So 50, 250, 1,000. So this is on a 65 by 65 grid. So it's about 4,000 coefficients originally. So the compression ratio is, I think it's something like 80, 16, 4 going from left to right. Okay, so that's the top row. On the bottom row, we just have the error. The middle row then is a representation of which multi-level coefficients we kept. So we kept them according to these weights that we saw in that theorem. So according to the ones that contributed most to the indicator, which means that to within constants, they contributed most to the actual norm. Here the norm being used is just the L infinity norm. So those coefficients that were most important, as sort of indicated by this theorem, are the ones that we keep. We discard the rest. So so here, remember that each multi-level coefficient is sort of assigned to, or like corresponds to, a particular node X in the mesh. So here, for each node X in the mesh, we've put a little black square if we've kept the corresponding multi-level coefficient, and there's no black square if we've discarded the multi-level coefficient. So here, hopefully you can see sort of the adaptivity of the algorithm. So looking, for example, here in the middle row, the rightmost square, we can see that the multi-level coefficients are like preferentially retained in areas of the domain where something is happening, where there's some interesting feature of the data. Basically, if the data is smooth and flat, you require very few multi-level coefficients to resolve that region of the domain to within your error tolerance. It's where you have like a peak or a trough or something is changing that you want to dedicate your multi-level coefficients, make sure that you resolve those features. Okay, Christoph, could we play the video now? The Brustleiter video. Okay, thank you. Okay, so again, every frame is sort of the same as the figure we showed. So hopefully you can see that now, as I should say, there's Chris, I'm gonna need you to play this a few times, so I need to explain things if you could. So whereas in the figure we had a sort of prescribed compression ratio, we said we're going to keep only 50, 250, whatever it was, of the multi-level coefficients. Here, for each frame, we're keeping a different number of coefficients. We're instead meeting a constant error bound. So on the top row, this is I think again it's L infinity error, so a 10th, a 20th, a 100th, and 0.005. So, excuse me. So depending on whether sort of something is, whether the reaction is sort of busy or not, whether the concentration is about constant, you'll see that, for example, now there's very few multi-level coefficients kept. This middle row looks like not very well. As I say that, it starts to change. So let's see. As the simulation plays, look for region. For example, now relatively few multi-level coefficients are being kept. There's very few black squares. That's because the coefficients, the concentration of the chemical, which is our data set, was at that time about flat. So we didn't need very many of the coefficients to meet the error tolerance. On the flip side, for example, now, where the reaction is very active and the concentration is like highly variable over space, if we had kept only this smattering of coefficients, we would have under-resolved all those peaks, and we would have incurred like an unacceptably large error. So hopefully you can see that again, it's an adaptivity. So at times where your data is smooth, you can get away with a higher compression ratio, but then the algorithm is able to sort of dedicate more resources, lower the compression ratio, but in order to keep the desired error tolerance. Okay. Christoph, I think we can now go to the next slide. Thank you. Okay. Let me continue. Okay, so in that example we showed that was L infinity error. So it was preserving this concentration field pointwise. So I had said at the beginning that often actually I think that's not what you want to do, and you can get better results if in fact you sort of compress using a smarter norm. So here's an example of how we can use MGARD to do that. So suppose that the thing you care about is not the raw values of the data in themselves, but some derived quantity that you're going to compute from the data. So here, this curly Q, it's a linear functional defined on your function space. It could be something like a surface integral, or say a convolution, something like this. And so what you would like is that here, when we compress this, when we calculate this derived quantity using the original data U, that's like the thing we really want to know. We've thrown away U, we've replaced it with U twiddle, the compressed data set. So we would like that the derived quantity when computed on the compressed data set is very close to what we would have gotten had we computed it on the original data set. So here, because Q is linear, the error here is given by the functional applied to the compression error. So we can bound this by the operator norm of Q and then the norm of the compression error. So here's where a sort of decision is made. So depending on the sort of properties of the derived quantity, we might want to use a different operator norm here, and it translates to compressing U in a different way. So for example, well, actually, I have two examples, so it's probably easier to actually see things. Okay, so here's a simple example where this is again a Brusselator example, and we just wanted, suppose we just wanted to visualize the compression, rather the not compression, but concentration field. So suppose I know I said that this is actually on a 65 by 65 grid, but in principle, suppose it's 65,000 by 65,000, but we're just visualizing it. We don't need that resolution. So rather than trying to plot the 65,000 by 65,000, we're just going to make like 1,000 by 1,000 grids, something like that. We're going to have a pixel, and each pixel is going to be like the color of the pixel is going to be computed by taking averaging the corresponding little region of the domain. So it'll be a little box of like n by n pixels, n by n grid points that will contribute to one pixel. So what this corresponds to, say mathematically, is saying, okay, my derived quantity is the average of my my data U over some little pixel of the domain. And I don't care that my individual nodal values are right, because I'm not actually seeing those in the visualization. I'm only seeing the averages. So I'm sort of saying to the compressor, you can get the nodal values wrong as long as you get them right on average, and my pixels will be the same. So okay, so then the analysis, which I won't write out, but I can just sort of describe. If you care only about averages of your data, what this translates to is saying that you don't care about, you're unsensitive to errors in very high frequency modes of the data. Because if you take a very high frequency oscillation and average it over some pixel, it'll be basically zero, because it's very oscillatory. So you get a bunch of cycles and it'll cancel each other out. So this is saying that when we are choosing how to quantize our coefficients, we can take the coefficients that correspond to sort of the narrowest and most oscillatory of these sort of wiggles, and we can afford to incur larger errors in those, because we know that those errors won't show up in the specific analysis that we're using the data set for this time. Okay, so here's an example where we can afford to throw away sort of the more oscillatory modes, and we have a mathematical guarantee that it's not going to affect the results of our visualization. Okay, then a more complicated example where the reverse is the case. This is data taken from SRD, which is a turbulent combustion code. The output that we're compressing is a flow field. So one way that the scientists sort of interact with the flow field is to make these things called streamlines. So you inject a sort of like a virtual particle in the flow field and have it just be like advected through the flow field, and then you use the trajectory it traces to visualize sort of what's going on. So we said, okay, on the left we have the streamlines as calculated with using the original flow field, the uncompressed flow field. On the right is the result we get from our compressed flow field. The compression ratio is about 1700. So we did a sort of similar analysis of this derived quantity. So here the derived quantity, it's not a spatial average. Instead, it's like the path taken by this massless particle as it gets pushed by the flow field. It turns out that is quite sensitive to the gradient of the flow field. Basically, because if you start to drift a little bit away from the true path, if the gradients are very high, you might sort of go much further away, which you don't want. You want to stay close to the true path. So in this case, let's see, you want to preserve the gradient. Higher frequency oscillations, the higher the frequency, the more it contributes to the gradient. Because when you take the gradient of something with high frequency, it's very large. So here, in contrast to the previous example, based on the quantity of interest, we compressed quite differently. So we gave special attention to the higher frequency modes because we knew that those were the ones that were going to really bite us if we incurred errors there with this particular derived quantity. Okay, so yeah, so this is a sort of little taste of how you can you quantize differently depending on how you're planning on using the data, and in particular, you can guarantee that these sort of like quantities that are somewhat removed from the original data are still sort of resolved correctly. Okay, okay, I have just one more example, and then hopefully I'm good on time. So just about everything I've shown you before has been on rectangular meshes, these sort of regular rectilinear grids. MGARD can also be used, I think, as I mentioned at the very beginning, also be used on triangulations. So There are some restrictions on the triangulation. As I said, you have to have this mesh hierarchy, so we can't currently support arbitrary triangulations, or also in 3D we can do tetrahedrations, if that's how you pronounce that. But even with this sort of the restriction on how the mesh is formulated, it does let us support a much larger variety of geometries. So here we're going to solve a reaction diffusion equation called the Gray-Scott system on a torus, just to show that we can sort of support things that aren't defined on squares or cubes and so on. So yeah, Gray-Scott equation is a reaction diffusion equation. We have these two variables u and v, and depending on these parameter values r, f, and k, you end up getting different patterns. So I'm going to show you two different patterns. Okay, so first I want to show this first trial is just to hopefully give you a little sort of picture of the type of artifacts that we get with MGARD. So here is our so for a particular set of these parameters in the differential equation, you can get this stripe pattern. So here's the original data about 600,000 degrees of freedom on this torus, and then I'm going to probably it won't well okay. Unfortunately, I get a little bit of a delay. In person, you can really flick back and forth quickly, but I'll go back and forth a few times. This is the picture we get when we compress down to 10,000 degrees of freedom. So it's a compression ratio of about 60. So I'm going to go back and forth a few times. I find it helpful if you look at just like a particular dot or something. It's a little bit easier to resolve. Hopefully you can see there is a bit of blurring. The compressed looks sort of rough, but nowhere do you see for example, spots joining to become stripes or stripes disappearing, or you're sort of like, I don't know, basically hopefully it's an acceptable amount of error. Yeah. Okay. So then right. And then here, same plot as before, the degrees of freedom, the 10,000 degrees of freedom that were retained. Something, since I have just a minute, I want to mention, this is not easy to see, but I'll just mention another case. We had said before, each multi-level coefficient corresponds to a particular node in the mesh. So it has like a sort of spatial bit of information. And so previously we've just talked about, we said like, oh, look, that you can see that the multi-level coefficients in a particular region of the domain where the function is changing quickly are being kept because they're resolving this like sort of difficult to compress region. But in addition, remember that the multi-level coefficients also have a level component. So each node sort of belongs to the node at which it was first introduced. There's a sort of the different multi-level coefficients encode sort of wiggles of different widths. As I said, it's sort of like a wavelet type thing. So something that you can't really see here because you can't see the coarse mesh, but you hopefully just sort of trust me that in addition to these retained multi-level coefficients sort of lying on the sort of the stripes, the region where things are happening, they also mostly are on the correspond to the coarser grid. So they're encoding the sort of wider, lower frequency modes of the data, and then only at like the edges of the stripes where the data is changing very quickly do we have to dedicate some storage, ultimately some bytes to these higher frequency oscillations. Okay, that might be a little bit easier to see in my last video. Christoph, could you please play the unstructured the .mp4 or whatever it is. Okay, so this is also a Gray-Scott simulation, also on a torus, just with a different parameter value. Yeah, and Chris, could you just play it a couple times as well again? So here, rather than these sort of static stripes and spots, we get these sort of like bacteria-looking things. It's like a moldy donut. So hopefully, so it'll restart, and so hopefully you can see, for example, at the back of the donut. I should wait till it really restarts, but I'll tell you what to expect before you see it. At the back of the donut, the blue spots have not gotten there yet. And you can see that only a very few multi-level coefficients are kept. And then in fact, those are on, they sort of correspond to the coarsest modes. You're just resolving the average because really the average is the data at the time that you don't have any dots there. So yeah, anyway, and then hopefully you can a little bit more easily see that actually as these spots move around, so here we're compressing each time step separately. So as the spots move around, the multi-level coefficients that are being kept sort of follow the spots. They're sort of like where the action is, and you're spending your bytes sort of representing only where sort of something is happening. Yeah, but so again, this is the sort of main point, or the way that this like differs from the brusselator. The reason I'm showing it to you is that this is being done not on just like a rectangular array, but on a triangulation. And so yeah, it lets us resolve more interesting geometries. Okay, Christoph, I'm done with the video. Thank you. And then, okay, so final slide. There are papers that go over the theory. These first two papers are sort of lay out the theory for how we can use MGARD to control error in derived quantities. That's the first paper. The second is generalizes the original papers, which talked about sort of rectangular grids to the unstructured case, the triangulations. The next two papers are neither of which have actually appeared yet, but they are coming out. Talk about some of the issues we ran into and algorithmic improvements and so on in porting the algorithms to GPUs and sort of just improving. The second paper actually isn't about GPUs; it's just CPU improvements and does a bunch of comparisons with MGARD with existing sort of methods. And then finally, we are releasing it. I mean, we have a public implementation. It's on GitHub. You can see it here. I would be overjoyed if anyone was interested in, even just if you can't compile it, that I would love to hear about it. Or certainly if you have any interesting data sets and you are thinking of compressing them and maybe you have interesting quantities of interest you need to preserve, anything like this, I'd be happy to hear about it. And thank you to the funding. It's a bunch of US Department of Energy projects. Yeah, thank you everyone for coming. I appreciate it. And please let me know if you have any questions. Okay, so yes, what about the impact on accuracy in certain situations? The drift has a severe effect on the results. So I am guessing you're maybe talking about the when you talk about the drift in these streamlines here. Yeah. Okay. So yeah. So this was a very difficult sort of quantity to preserve, because once you get off the true streamline, which inevitably like happens immediately, well, you know, assuming you don't have perfect reconstruction, it immediately happens. It's sort of, I remember the analysis was sort of like ultimately exponential in that like sort of anything can happen. I mean, eventually, you know, you have, and you'll do better if you resolve the original data better. So this was a very challenging one. We ultimately didn't have bounds of the form that, for example, okay, for all time, you know, if you propagate these particles arbitrarily long, they'll always remain within epsilon. We couldn't bound it that strongly. So you're totally right that just even a small amount of drift, it basically can compound. So the thing that we settled for in this case, which this was in the judgment of some people who had sort of had some experience with like sort of how these error grows, we sort of settled for, let's see, I think like it was for, you had to say for bounded time and your error could grow sort of, maybe even exponentially, but only for bounded time. There was some sort of limit in that if you accepted even a tiny bit of error, there was like some error term that immediately sort of killed you if you wanted to go for all time. So anyway, I mean to say definitely like it was, I think, appropriate for purposes like this, where ultimately what they were doing was using the streamlines to like visualize and understand the data. If you were trying to trace a particle, you know, as it like it's a combustion simulation, so it's like in a sort of generator. It eventually definitely just the errors grew too quickly. It was sort of like so demanding of a quantity of interest that we couldn't guarantee that for a long time. Yeah, to be honest, it's much easier to handle things that are sensitive to like integrals and averages, which this was sort of, you were integrating in one dimension, but not in the other. So yeah, it was, yeah, hopefully that answers your question. Let's see, my user get upset. Yes, what? Okay, hold on. Computational cost. Okay, so let's see, each of the central sort of operations, the interpolation, the projection, which involves projection involves multiplying by a mass matrix, solving a different equation, different system. Each of those are order n, and there are, or we have implementations that are order n, and also are in place. So then there are roughly log n levels in your mesh hierarchy. So overall, it's something like n log n. It gets a little more, I mean, it gets better in higher dimensions, actually, for two reasons. Excuse me. One is that all these operations, like the projections, you can decompose them into this tensor product of like tensor product of 1D projections, for example. Those can be done in parallel if you have an implementation that does that, which we are working on. We have a sort of prototype GPU implementation. The second way it helps you is that if you have n points split across like a 3D mesh, that log n factor is smaller. Your mesh hierarchy will be a little less steep. So yes, it is better in higher dimensions, although then you do run into more problems with this this sort of the like striding issue that the sort of quote unquote like physically adjacent nodal values end up being kind of far apart in memory. So you don't get sort of like all of the benefit, or we're working on like eliminating the gap there. Yeah, but it's like an n log n with a not trivial constant. So I don't have like a bandwidth number for you or anything like that. It's reasonably quick. It's not going to like chew through 10 gigabytes in a second or anything like that. But currently also a limiting thing, both to give you sort of an idea of the speed and also of sort of areas of improvement. The lossless compression is often it's again, I don't have a number, but like something like 50%-ish of the time, maybe. I maybe don't quote me on that, but it's so the and this is also, we pass it just directly to the off-the-shelf compressor. We're not doing anything in parallel or anything like that. So it's definitely, we would like to do the compression on the GPU, and then we wouldn't be held up by that. But currently, sort of, it's about on the time. So you have like a gigabyte data set, you do this transform, you quantize all this stuff, and then you ultimately compress a gigabyte using zlib. So it takes like, some small multiple of that, because that's something like 50% of the time. Okay, sorry, I should go through the questions more quickly. Real-time data acquisition. So I wonder if, something that, so an example okay, let's see. An example I didn't show, we have done this with compression in time, where we actually did with the Brusselator example. So we did a 65 by 65 in space times 65 in time. That worked great. We actually got better, maybe as you would expect, we got better results than we would by independently compressing each time step. The issue is you have to have all 65 time steps in memory. So it's basically treating time like just another spatial dimension, I suppose. Yeah, you don't maybe get credit for writing like a streaming method or anything like that. So something that we currently can't do, and I have maybe some ideas of how you might be able to do this in like a real streaming way, but I don't know for sure, is to sort of say compress in space for every time step, but then somehow stitch together some sort of third thing in time so that you're also reducing in time. I do think that with these transform coefficients sort of like do sort of capture something real about the data. So I do think, for example, you would get like good correlation one time step to another. But I've never, the experiment I've done was actually then to just compress in time as though it were another spatial dimension. Yeah. Okay, going to exascale, subjective choice. We actually did this for data with periodic boundary conditions and a fusion reactor recreating. Yeah, a surface plot. Yes. Oh, Scott, that's you. Okay, sorry. I was about to say, wow, that person I need to talk to. Scott's my boss, so that makes sense. Okay, deep learning. Could the MGARD algorithm be used for pre-processing of scientific data analyzed by deep? Oh, interesting. Okay, so three things, I suppose. That's something I haven't tried. I hope, yeah, I think it should work in that, sort of similar to when I've read papers about sort of like image classification stuff. It seems like a lot of the effort is going into like sort of finding the right features to start with. And so hopefully with that intuitive sort of explanation I gave of what the multi-level coefficients are really encoding, they're sort of maybe in a similar way encoding a sort of feature. It's like a sort of variation on a certain scale in a certain location. And so as a guess, it's easy for me to say like, yes, this might work. But as a guess, I would hope that the coefficients might sort of be more sort of a better sort of basis to learn on. But I don't know for sure. And then I do want to mention that reminds me of there's another compressor, scientific data compressor called SZ. It's not a transform-based compressor. It's more like PNG. It's like a prediction-based compressor. You predict the values as they come in, rather than doing a global transform. But they have a paper that I think is called Deep SZ, where I think they look into like sort of pre-processing the data with it's some interaction. And maybe let me not misrepresent it, but yeah, something that might be of interest. And then the second question: could the operator norm used to determine how data is compressed be learned by gradient descent? In such case, perhaps MGARD uses a layer in a learn network or as a component in a deep learning algorithm. Okay, yeah, an interesting question. Yeah, so currently, that's a really good question. Currently, the computation of that operator norm is very expensive currently, because you need to apply it to a basis of the entire function space, which you could do in parallel. But then you need, and then you sort of anyway, it involves many applications of the functional. So granted, many functionals only operate on like a local. They're not sort of order n. They're like order 1 operations. Like say for the pixel example, you're just doing an average over a small location. So it might be actually quick if you wanted to brute force do that. But so currently that is done in a very slow way. And the way this is actually, and so something that I have thought a bit about, and it would be good news to me if you can calculate something like that using gradient descent, is a way to calculate that quickly, because currently in practice, the way we use that sort of quantity of interest control is usually sort of more pen and paper. So for example, with this S3D streamline example I have up here, we didn't calculate the operator. We didn't calculate the operator norm at all. Actually, so we didn't, for example, take every potential particle, like advex them all, look to see at the errors. Instead, we wrote down, okay, how are they computing these streamlines? It's like a path integral. Path integrals sort of depend on sort of how much smoothness in the data, what can we afford to throw away? And so that, for example, here, rather than getting like an actual sort of result at the end, which is like, and the streamlines will be accurate to within epsilon. The actual way we used this, and I for the sake of space, I didn't do a comparison, but we actually we said I'm going to compress it with different smoothness parameters S. So the thing we found using the analysis was you need to preserve the gradient. So we chose S is equal to 1, and we did compression ratio of 1700. And then we did the same thing, but with S is equal to 0. So I remember S is equal to 0 is just the L2 norm. So you don't have guaranteed control of the error. In general, your error in the you don't have guaranteed control of the gradient error. You do have guaranteed control in the L2 nodal error. And so yeah, I maybe should have shown it. I didn't for space, but so rather than sort of ending using a sort of like numerical, like getting a number at the end for this approach, we said for given compression ratio, if you use a different smoothness parameter, we compared the streamlines we got with the S is equal to 1 and S is equal to 0 cases, and indeed the S is equal to 0 cases, like basically you lost some resolution. You didn't sort of like resolve the proper behavior of some of the streamlines. So anyway, if and the reason we didn't do it numerically is because it's such like we didn't have a quick way of computing this operator norm. So I don't know for sure, but it does seem like there should be a faster way of computing this operator norm than what we're doing. And if we could do that, we could sort of apply this a bit more concretely. Yeah. Okay. I have given at least some answer to all the questions I've seen so far. Please let me know if I've missed anything.
You switch one thing and another one is changing. So can you hear me now, Ben?
Yes.
Thank you. Great talk.
Thank you.
I have only seen cases of deterministic equations, some sort of evolving in time. Can you apply those methods for non-deterministic or sort of arbitrary situation of data on the grid?
Yeah, so certainly, let's see. Yeah, this is all deterministic because I needed to come up with the data sets myself. So yes. I solved some PDEs. That was sort of my background. Let's see. So I want to think. I'm thinking we have applied it to other data sets. I'm trying to think if any of them had a specific like stochastic component beyond just having noise in them. I am not positive I have. Certainly the algorithm doesn't know any. Well, I mean, yeah, the algorithm is sort of agnostic to the source of the data. So whether it's observational data, like simulated data, random data, it treats all of that the same. So I mean to say it definitely could be applied to stochastic data. But the flip side, I suppose, of that is because it's not treating things any differently, it doesn't, it doesn't have any sort of like, how do I say, sort of knowledge of like stochasticity. It couldn't take advantage of anything particular to random data, because it doesn't know sort of anything at all about the source here.
Another question, which sort of it's completely outside of my domain, but there's kind of rings a bell. Those situations, is it possible to connect in some sort of deeper level this compression scheme with some sort of ergodic theory? The system that you really can average over the domain, spatial domain.
Let's see. Okay, so I'm gonna sort of answer a question that I hope is close to yours, because I know very little about ergodic theory. But the connections I've seen is there are results in approximation theory, which possibly I'm remembering has some connections to ergodic theory, where there's also an approximation theory which say something like, if you want to approximate your data in a particular norm, how many, let's see, it's called like n-width results. So it's saying sort of how many, the sort of like discrete example is like you have a ball in Rn and you want to put a lattice of points on the ball such that every point in the ball is close to a lattice point in some given norm. Right. Yeah, as I'm saying this, I'm now remembering, well, I'm if I ever remembered how I thought there was a connection between approximation theory and ergodic theory, it's completely escaped me now. So so I don't know, I guess would be my answer. Yeah.
Yeah, because that's I remember a few years back we've talked with Scott about noise and data and loss and entropy and things like that. Big keywords.
Yeah, right.
Extremely sort of interesting, on the deeper level.
Okay. So yeah, the one thing I've seen which maybe relates to this, this had come up in a talk with some fusion scientists recently, where they were trying to compress particle data, or let's see, the data that they had was particle data, but they said that it was really like there was some sort of like ergodic thing where what they cared about was actually the sort of the like long-term distribution. Like the particles are essentially like samples from the thing they actually cared about. Yeah. And so this actually goes back to like way at the beginning of the slide. I had talked a bit about I had talked about some like ad hoc compression methods that some people use, like downcasting from doubles to floats. But some people are actually using some fairly like physically involved compression methods. For example, if they have a particle and cell code and they have particles and they would like to keep the particles, but there's way too many. So instead they sort of keep like an electromagnetic field that is sort of induced by the particles. And so I wonder whether my impression of my recollection of what little I know about ergodic theory has to do with sort of like trajectories and sort of like the long-term distribution. Right. And so it's one of these things that like, and so this is something that I think if you have like that level of, I mean, in fact, probably people who have data sets, they know like quite a lot about the data set. So actually, I think probably there are real opportunities to use this sort of like specific physics of your data to compress it. Where here with MGARD, you're doing I mean, it's mathematically rigorous and stuff, but it doesn't know anything about, for example, like the specific differential equation of your data or like whatever dynamics your data might satisfy. If there's some, for example, like, it doesn't, I mean, there's any number of things, I suppose, but for example, maybe like there's a very important that your data remains positive or something like this. There's a lot of these sort of like, in my mind, sort of like physical things. And the goal, I think, is to like incorporate as much as that as possible into the compression technique. One, because you'll get better performance, but then also it's a lot easier to preserve these sort of things that the mathematician has maybe never thought about. So for example, it never really occurred to me to say like, oh, actually what they really care about is sort of say like this long-term distribution of the dynamics. That's just, I barely had even heard of that. So there's ideally that type of information would be incorporated, and I think you could get better results from it. Yeah.
I don't see any other questions, so maybe I will ask another sort of question. Maybe it's relevant or not. You have shown a couple of interesting equations, sort of diffusion or sort of versions of this.
Yeah.
How have you thought about using this for Newton's equation for molecular dynamics? When you have, you know, massive number of particles, like in biochemical situation.
Yeah. So currently not with this project, because for this project we need to have, it needs to be like field data. However, my advice, I know people involved in the larger project have talked about particle data. It's way back. My advisor, Mark Ainsworth, I don't know, it's many slides back. I know has taken an interest into this. So currently, currently you can't use MGARD for particles because you need to have, for example, like a mesh, and you need to, there's no sort of like sense of like, or like notion of sort of, for example, tracking particles like through time and it being the same particle type of thing. The things I have, so yeah, it's an ongoing project for him. I don't know really what approach he's taken. The things I've heard about approaches is sort of like ultimately about converting it to some kind of field data, or really just like how do I say, approximating the distribution, but like say with some like mixture of Gaussians or something. But that does then run into the thing that I think maybe is lost there, or something that effort would have to be put in, is you maybe then don't have guarantees of, like you're saying, there's like some, I mean, there's like mechanics of it. So for example, you might, you know that it like obeys Newton's laws, you know that you have, for example, like mass preservation, or say your flow maybe is like divergence free or something like this. And this is the type of thing that we would really like to be able to preserve these sort of like physically meaningful. I mean, in addition to all these, I was talking about these sort of specific quantities of interest, you know, the integral of this or that. But we also would like to be able to preserve these sort of like concrete physical invariants and have some sort of like knowledge of that. But MGARD currently is too sort of like general purpose for that. It's sort of like is in the world of functions defined on meshes. Yeah.
Okay, thank you very much, Ben. Thank you for your talk, and thank you for answers to all the questions from the audience. Let me just remind me again that we will have a next seminar on the 18th of March. Let's see the slides, if you could show the slides of this event, please. Right. So this is the seminar. I welcome all of you, or if you can't attend, please spread the word. As I said, that would be very interesting from the point of view what sort of facilities, infrastructure, and services should be put in place in order to create a environment, a research environment at the university that is that responds to current digital needs of researchers, academics, and students. So we'll see how this has been done at the University of California, San Diego. And I also encourage you to check the website of our conference. Right now it's very, very basic, but we've already announced there's a call for papers. So if any of you might consider submitting, or again, we need friends to spread the word and advertise. And today we've heard Ben Whitney from Oak Ridge National Laboratory. I thank Ben, and I thank all the participants, and I thank those who ask questions, my friends from various places around the world. Thank you for coming. And with this, goodbye to the next month. Bye-bye.